Okay, welcome everybody to the second talk of today. So, Irit, are you ready? Maybe. We're not echoing.
Actually, I don't hear though. Do you hear me?
Can you hear me now?
Okay, I guess if you hear me, then I can. Should I start? Thanks. Okay, I'm sorry about all the audio glitches, but thanks for the patience. Okay, so we were talking about random walks on various dimensions in a simplicial complex, a high-dimensional expander. And now I'm gonna look at these two theorems that say that if a complex is a link expander, remember what this means is that for every face, you look just at the local view, the part of the complex just above that face, and you look at the graph underlying that part. That graph needs to be a lambda expander for every one of the links. This definition implies that the complex is a lambda random walk expander, and the definition of being lambda random walk is that the upper and the lower random walks are very similar to each other when you remove the laziness component. Okay, so really this is an if and only if, except that in the only if you lose some amount, and I don't know, maybe very likely that this can be improved, but I don't know what is the best possible connections here, so that's something to explore. Anyway, let's just look at this first part, which says if you know you're a link expander, you can deduce that you're a random walk expander, and this direction is proved very useful. It was used in the breakthrough result of showing that certain Markov chains on an exponentially large state space converge in polynomial time. This is by Nari, Liu, Vescaran, and Weizmann, showing that the basis exchange random walk converges. I'll talk about that soon. Anyway, let's first prove the theorem. If you're a link expander, then you're a random walk expander. So let's start. And really the proof is, again, using or showing the local to global principle that underlies a lot of this area, showing that if you know something about the links, you can deduce something much more global. Okay, so we start with a function in Ci, so it's a real valued function on the I faces. And I needs to be, the dimension I needs to be smaller than D so that we have room to go up. We need to say something about the upper random walk being similar to the lower random walk. That is the conclusion we are looking for. Okay, we want to show that X is a lambda random walk HDX, so that upper random walk is similar to the lower random walk. Okay, so this is what we need to show, that Mi plus F inner product with F, this quadratic form, is upper bounded by UD F inner product F. UD is the lower random walk. You go down D and then up, plus some error term, which is the lambda. I guess sometimes I called it lambda, sometimes gamma, but it's the same. Okay. All right. Okay, maybe I'll change. Let's see if I will change it, and hope I don't run into a lot of trouble. Okay. So first, let's write down the expression for the Mi plus. So basically, it's an inner product on the I faces. Oops. I faces. So you take a random I face, and then you write F of S times this whole expression is really Mi plus F of S. And what this is you need to take expectation over, go first up to a T just above S, and then you go back down to an S prime just below T, but you need to take care that S prime is not equal to S. And that's kind of the random neighbor you go to when you do Mi plus, and you average F on this random neighbor S prime. So this is just kind of spelling out the definition of Mi plus. And now we want to write it slightly differently. So let's first see that this distribution is the same as if we first chose T, the one dimension higher face, and then we chose two faces below it, S and S prime. So it's just the same distribution. First you choose, say, if you want, you can think of the situation where I equals 1. So you're walking from edge to edge. First you're walking from edge to triangle to edge, and later we'll walk from edge to vertex to edge. So then you first choose an edge, then you choose a triangle containing the edge, then you choose another edge in this triangle that's not the original one. And it's the same distribution as if you first choose an I plus 1 face, a triangle, for example, and then choose two I faces, inside of it, one edge and another edge. Okay, it's exactly the same. And now, look at this drawing that's supposed to help us. This circle here is supposed to be the entire face T. So it's an I plus 1 face. It has I plus 2 vertices in it. And I chose one choice of S is just removing some element from T. So T minus X. And then S prime is some other I face. So it's removing some other element Y. Okay, this new feature of notability, I'm not yet adapted to it. So it's S prime. So basically what you're doing is you have a I plus 1 face. First time you remove X, second time you remove Y. And let's look at the remaining part. Let's call it R. So to choose T and then S and S prime is equivalent to first choose R, the remaining part, then enlarge it to T by choosing some random XY such that together with XY, you get a face. This is just the same as if you first choose the face R, and then you choose a random edge from the link of R, right? Because what is a random edge from the link of R? The edges in the link of R are exactly coming from faces that contain R, that when you remove R from them, you are left with an edge. So this is the conclusion of this is that choosing T, S, and S prime is the same as choosing first, apologies, is the same as, I guess, let's do it this way, first choosing R, and then choosing an edge in the link of R. And then R union X is S, and R union Y is S prime. So far, we only have equality. Okay, now this is interesting. We started from S going up and going to S prime, but now we have something below. We have R, which is actually an I minus 1 face. So we can now look at this whole expectation from the R's, right? So what's going on now? For every R, let's define F sub R at a point X to be F at R union X. Okay, so now we have a function just on the vertices of the link XR. We had a function on the I faces, and now we have a function on the vertices of the link XR. Okay, so now with this notation, this expression just becomes the quadratic form AR FR, inner product FR, where AR is the adjacency matrix of the link of XR. Okay, again, still equality. So now we can use the fact that we know something about the expansion of the links. We actually know that AR is a very good expander. So this inner product, AR, FR, FR, is pretty similar to another inner product where instead of AR, we can write, you know, the J, the kind of complete graph quadratic. Okay, so this is exactly the gamma link expansion. So here I see that I still have gamma. I'm not going to get away with it. So let's interchange gamma and lambda. Okay, sorry about that. It's the same number for us. Okay, so by our assumption that, the one-sided assumption says that AR is less than in the Loebner order UD0, this is just another notation for J. This is just another notation for J, and then plus the error term, which is gamma. So we get this this expression. And now, remember we said that U and D are joined to each other, so I can take this U and move it here, and I will get df times inner product df. So this is just df at point R. It's basically you average all the points of f sub R, and then you take the square of this average. This is exactly what the matrix J does. So this term just gives me dfr squared. And this term, when I take expectation over R, I get just the 2 norm of f altogether. And so all in all, what I got is the lower random walk, UD, F, inner product F, plus this error term, which is exactly what we wanted to get. So we saw that to bound mi plus F comma F, from here, we ended up with the lower random walk, plus this error term, and we did it by locally at the links having the same kind of inequality. So it globalized. So that's really like a proof that writes itself. Okay. Now let's look at this application to the matroid basis exchange random walk. Okay. So this is another example of a simplicial complex that I didn't describe to you. So let me describe it now. I should have kind of erased stuff so that we don't get distracted. Okay, so we're gonna now not look at general matroid, because then I would have to define it. Instead, I'm gonna just look at the following random walk that moves from spanning tree to spanning tree in a given graph. Okay, so I'm starting with some graph G, okay, with n vertices and m edges, and I'm building a simplicial complex. What is my simplicial complex? Well, the vertices of this complex are going to be E, the edges of the graph. Okay, so m vertices, and it's going to be a high dimensional complex. The dimension is going to be n-2, because the top dimensional faces are n-2 faces. These are sets of n-1 edges, only those sets that form a spanning tree in the graph. Okay, so we defined a bunch of faces like this. And now that I defined the n-2 faces, I take all their subsets, I close downwards, and every forest or every subgraph that has no loops, it always can be completed to a tree, so it's a face in our complex X. So that's the definition of a complex. And now here's a random walk. You start from some arbitrary spanning tree, and you start changing it. How do you change it? Well, you go down. When you go down, what are you doing? You're erasing an edge from the spanning tree. Okay, so now you have two components. Now you can add some edge. There's maybe more than one possibility, so you add it. And you keep going like this. What is going to happen? Are you going to reach any other spanning tree? So actually you can easily think about it, and you'll see that yes, you will reach every other spanning tree. But how fast will you randomly, you want to converge to kind of a random spanning tree. How fast will that happen? I mean, there could be an exponential number of spanning trees. Okay, so this is how we're gonna now use the theorem that says if you study your links and you know that you have a good link expander, then you'll be able to deduce that the random walk converges. Okay, so let's now look at these pictures. So I took this graph. I'm sorry that the picture is so weird. And I'm starting from some spanning tree. So the blue edges are a spanning tree in this graph. Now I want to understand the links. So my top faces are spanning trees. Well, I can look at the link of one below. So when you erase one edge, but that's like, it's like looking just at one dimension before the top. It's not interesting. The link of such an object has just a bunch of vertices. So that's not interesting. When does the link become interesting? When the dimension is 2 below. So you need to go from n-2 to n-4. So here is, for example, an n-4 face over here. I took a spanning tree, this one, and I erased 2 edges from it, right? Which ones did I erase? I guess, oh, well, I erased this one and this one, right? Okay, so I erased two faces from it. So now I'm in a codimension 2 face. So it's the top dimension -2 face. And now let's look at the link of this thing. So I'm doing it by example, but you will see the idea. So I need to understand the link of this thing. So remember, the vertices of our complex are the edges. So who are the vertices in the link? They're all the possible ways of extending this forest into a spanning tree. So basically, I should never add an edge that's inside a component. This is not allowed. But any edge that crosses between components is allowed. So I have these 2 edges that cross between component 1 and 3. So you see here that I have 3 components, right? 1, 2, and 3. And now I have 2 edges crossing from 1 to 3, 2 edges between 1 and 2, and actually 4 edges between 2 and 3. Okay, so the vertices in my link are these edges. So I have 2 edges. These are vertices in my link. So I have 2 of the red kind, 2 of the blue kind, and 4 of the purple kind. Okay, so these are, 2 + 2 + 4 vertices in my link. Now, who are the edges in my link? So what is an edge in the link? I'm going to allow myself to connect, one of the vertices to another one of the vertices if both of them together live in a spanning tree. So when will 2 edges live together in a spanning tree? Well, once I add, say, the edge between component 1 and component 3, I'm no longer going to be allowed to add another edge between these 2 components. So this edge cannot be in a spanning tree with this edge, but it can certainly be in a spanning tree with any one of the other edges, right? Because if I add this and this, I have a tree. And if I add this and that, I also have a tree. So this edge, one of these 2, is actually connected to all the other edges except for the red ones. So all in all, what you have here is a 3-partite graph between the red, the blue, and the purple. And every edge of the 2-3 kind is connected to every edge of the 1-3 kind and every edge of the 1-2 kind. So what you have here in the link, this is the structure of the link, and it doesn't matter which 2 edges I erased. It's always going to be a 3-partite graph. The size of the parts is not always the same. That's the only variability we have. And if you look at the second largest eigenvalue of this graph, it will be 0 or less than, or at most 0. I don't remember exactly, but definitely no more than 0. And so by the trickle-down theorem that we saw, even when you go down in the links, if you started with 0, then 0 divided by 1 - 0 is still going to be 0. And so you get that the entire complex will have expanding links all the way down. We only looked at the top links. And so by because of this, actually, maybe you don't even need that. It's enough to have link expansion at that level to know that the random walk on this level converges to, very fast. Like the gap there is polynomial in the dimension. So it's going to be 1/n maybe, or something like that. So in polynomially many steps, you're going to reach a random spanning tree. So of course, this is a bit hand-waving, but you get the heart of the idea of this beautiful result that uses the analysis on the links to show that the random walk converges. Okay, now I want to talk a little bit about the posets. Okay, so far I talked a lot about simplicial complexes, and most of the theory of high-dimensional expansion was developed in this context. There's two reasons, I think. One is that it kind of grew out of this LSV complexes, these Ramanujan complexes that are simplicial. And two, which is probably more basic, is that the notion of a link is the most natural and kind of pretty in the simplicial world, because then you can really remove a vertex and you'll still have a face, and so things work out nicely. But simplicial situation is restrictive, and a lot of high-dimensional objects are not simplicial. You can think of more general situations, and I think a poset is one possibility. So we're gonna copy the same kind of picture that we had for the simplicial complex, where we had x minus 1 was some trivial element, and then we had elements of rank 0. In the simplicial world, these were vertices, but we can have another poset, for example, the poset of linear subspaces. So these would be zero-dimensional subspaces, maybe affine, like points in a vector space. And then you can have elements of rank 1, for example, affine lines. And then you can have elements of rank 2, affine planes. That's one example of a poset. Another example of a poset, we have these objects called the cubical complexes, where you don't have triangles, but rather you have vertices, edges, squares, cubes, and so on. So that also gives rise naturally to a poset, partially ordered set, maybe I should have said. And a lot of the things that we were looking at, we can just as well define on posets. So first, you can certainly define the up and down operators, right? When you want to, you have a function on the I faces. These are the elements of rank I in your ranked poset. Then you can apply a down operator and create a function on the I minus 1 faces, where you define the function on some I minus 1 face by averaging the function on all the elements above your element. And you can also apply the down operator similarly, or the up operator similarly. Sorry. And you can define a random walk, where you start from an element, you go up, then you go down, then you go up, then you go down. So everything that we did, you can do in the random walk part, you can do on a poset. And a nice part of the theory actually carries over to this setup. So not going to talk about it anymore. I just wanted to say that, for example, you can find a Fourier-like basis for functions on the I faces using the same ideas. And you can define what it means to be a high-dimensional expanding poset. Okay, so now in the last part of the talk, I do want to talk a little bit about the second kind of expansion that is studied in the area of high-dimensional expansion, and this is coboundary and cosystolic expansion. Now, it used to be maybe a few years ago that we said we would hear a talk about high-dimensional expanders, and the talk would begin like this. It would say, you know, for expander graphs, there are multiple definitions. There's a combinatorial definition of edge expansion. There's a spectral definition. There's a random walk definition, and so on and so on. And they're all the same for graphs, but somehow they all diverge to different definitions when you generalize them in higher dimensions. But somehow things are a bit less divergent these days, and I think there's two main kind of types of definitions. The first one is the ones we've been talking about so far: link expansion, random walk expansion, and we saw that they're related. Although the relationship is not completely clear, there are some questions. And there's a different type of expansion, which is this one. And this has to do much more with the topology. It's kind of cohomological, and it has to do with linear algebra. So the way to think about it, I think, is you use the geometric structure of the complex to create certain linear algebraic maps. Okay, you use the incident structure to define certain linear maps. So now you're working, say, over a finite field like F2. You can work over many different coefficient spaces, not only F2, but F2 is a good place to start. And then you define these maps, this delta and this partial. And where the tail goes is supposed to indicate to you, like, how delta, the tail goes this way, so you're going up, whereas partial, the tail goes this way, so you're going down. So really, this is like an up, and this is like a down. And the formula for defining delta F is exactly the same formula that we had for the up operator. So let's see what's going on. Firstly, we define the I chains. Now it's not like we did before. Previously, Ci was the set of all functions from the I faces to reals. Now we're looking at Ci is just the set of, well, let me even write it this way. It's just F2 to the Xi. But I could have written as the set of all functions from Xi to F2. It's the same. So it's almost like we had before, except now we replace the reals with F2. Okay, but somehow this changes a lot. So delta takes me from an I chain function on the I faces to an I plus 1 chain, moves me up. And this delta part, the partial takes me, this is the boundary map, it takes me from an I chain to an I minus 1 chain. So this is called the boundary map. And this is called the co-boundary. So somehow, boundary is maybe more intuitive, but co-boundary is where all the interesting things happen. So I'll talk about it some more now, but I want to just say that it's somehow more mysterious than the previous part of my talk. These maps, we already saw that they're useful. You can get from them locally testable codes and kind of interesting definitions of codes. You can get from them quantum low density parity check codes. So there's some interesting things happening with these maps, but they're much more mysterious. And also they're related to these topological notions that have, topologists have good intuition for them when you're working over, the complex numbers or the reals, and less intuition when you're working over F2. So it's kind of a good area to, if you're a student and you're starting, it's a good area to enter because it's growing there. We don't yet understand what's going on. So there is maybe a lot of things to discover. Okay, so let's do some definitions, right? So I already wrote the bound, oh, sorry. I'll call it on. Okay, are we back? Just a minute. Apologies. Okay, so the boundary and the co-boundary operator, we described them, and let's, for example, focus just on the co-boundary operator. Okay, it's a lot of things, so it's best to restrict our focus a little bit. So we're going to be talking now about the co-boundary operator. So what's going on is you have an I chain. So F gives you a bit for every I face. You can think of I equals 1, for example. So F gives you a bit on every edge. And now you're applying delta. So you're going to get now a bit on every triangle. And for a triangle, what is the bit that you're going to get? Well, you're going to sum the bits on the 3 edges. So previously we said, let's average the numbers on the 3 edges, but now we're working over F2. So we're just going to sum them, mod 2. Okay, so every triangle now has really the XOR of the 3 bits of the 3 edges. Okay, that's what delta does. Okay, now something interesting happens, which is that when you apply delta twice, suppose you start from a function, say, on the vertices. You apply delta once, you get a function on the edges. You apply delta again on what you get a function on the triangles. But now you will get 0. What's going on is that every value will be added twice. So somehow they will cancel, everything will cancel, and you will get 0. Okay, and this is something that is inherent in this entire theory. This is what makes a chain complex. So you get this sequence of arrows. People like to draw it like this. And the meaning of this chain of 2 arrows is that the image of delta I minus 1, so you start from something over here. You apply delta once, you get something that's in the image of delta I minus 1, and there's a name for this guy. This is called BI. This is called, sorry, BI minus 1. BI, sorry. This is called BI. So why is it called BI? BI are things that come from one layer below. These are the co-boundaries. B is for boundary or co-boundary. And the index I indicates that I'm sitting inside level I. So these elements are I cochains. Okay, so I started from Ci minus 1, I move 1, I'm now in the image in BI. Now I take my element that is in BI and I apply delta once more. Okay, I'm going to reach 0. So that means that I'm in the kernel of delta I. Okay, and this guy is called Zi. Okay, so these are just names. BI is a name for the image of delta, and Zi is a name for the kernel of the next delta. Okay, these are called, let me say, these are called the so it's a bunch of words. It's not important to remember them right now, co-boundaries, but I'll say them just once so you know. And these are cocycles. Okay, so for me, I think the important thing to think about first time you hear about these things is that you have here a chain of 2 maps, and you know that the image of the first is inside the kernel of the second. Now, how to think about it? One way to think about it is that being in the image of a map gives you kind of, there's an explicit way of constructing these guys. You take something in Ci minus 1, you apply the map, and you get something in the image. Being in the kernel of a map is an implicit definition. You need to find something, I don't know how, and when you apply the map, you're supposed to get 0. So you're sort of, you need to find something in the kernel of the map, okay? So it's harder to do, right? I mean, if it's a linear map, you can do it in quadratic or time, but in general, kind of being in the kernel is something that's less explicit than being in the image. Okay, so okay, that's one thing. Now we'll give some examples. So sometimes actually BI equals ZI. In this case, you have 2 different descriptions of the same space, one as an image of something and one as a kernel of something, but sometimes they're actually not equal. And then you define the quotient space, and this is the cohomology. Okay, this is the space of elements that are really new. They're items in the kernel that don't have a pre-image. They're really like new things that come up. Okay, so this is the cohomology. Okay, so far it's not very meaningful, but let's look at a few examples that connect between these abstract notions and really nice combinatorial properties that we are familiar with. Okay, so let's just calculate a few examples. First, maybe if there's any questions, then. Okay. All right. So let's start with a few examples, but I want to say the following thing. In general, you will see in many situations in topology or in math, you will see a sequence of arrows like this. And it's called a chain complex. So it's like, if you see just one arrow, you have a linear map. If you have a sequence of arrows, it's like a high-dimensional linear map. Just like, you know, if you have a graph, you have like the arrow from vertices to edges. But if you have now a two-dimensional graph, then you have vertices, edges, and triangles. So you have like two arrows. So this is more general. You can have a sequence of arrows for linear maps, and this is called a chain complex. But we're focused on a much smaller sub area of this, where our chain of maps, they come from some geometric object. We have a high-dimensional expander. We have a simplicial complex. It's some combinatorial object, like all the ones we saw, with the matroids or with the spherical building, or this fish guy. So you have some concrete simplicial complex, and you use this object to define your chain of linear maps. Okay, and that's really cool because you can then use the geometry, and also you can use like analytic power that you've learned from studying random walks and from studying link expansion to reason about these linear maps. And this is really what's going on. We're used to it, that when we study, PCPs or constraint satisfaction problems, we study discrete objects using real analysis, right? So the same thing is going on here. You have these linear maps. They're defined on this geometric object, and you study them both by using linear algebra and also by using analysis. So we're not really going to see it in this talk, but maybe in Max's talk we'll see. So okay, let's now again. So now we're doing examples. So in our mind, we should think of, we have some simplicial complex, some picture, with vertices and edges, and maybe I have it down here. Yeah, here is an example. You have vertices and edges and so on. Okay, maybe I'll move it so we can have it in our mind, like this. Okay. And now we're gonna understand what these deltas do on this object. Okay. So my spaces are going to be C-1. This is all the functions on faces of dimension -1. So there's only one face of dimension -1. It's the empty set. So C to the -1, this is just equal to F2 to the, singleton. So it's just F2. Okay. And C0 is F2 to the X0, right? So it's X0. Okay, so it's like all the 0-1 labelings of vertices and so on. Okay, so now let's look at my first example. I'm here. Suppose I have some function in C0. So this function gives me a 0-1 value for every vertex. And since it gives me a 0-1 value for every vertex, I can use the letter capital S to say this is the set of vertices that get a 1. And the other vertices get a 0. Okay, so my function really indicates some set of vertices, like, maybe it indicates this set of vertices. Now, what is delta F? So I don't really need to write 0 because I know that F is in C0, but if I want to calculate what is delta 0 of F. So delta 0 takes me from C0 to C1. So it's a function on edges. And I need to now for every edge, I need to calculate the function on this edge. It's really the sum modulo 2 of f on this vertex plus f on this vertex. Okay, so suppose that my function, how should I do this? Yeah. Suppose that my function f was, it was 1 on this set, on just these 3 vertices, 2, 3, 4. By the way, in this picture, it's misleading because 2 and 3 are pictured here twice, okay? Because the picture closes. But anyway, suppose this is my set S, the vertices 2, 3, 4. And now I want to know what is the delta 0 of f. So it's really, well, this edge gets 1 plus 1, so it's 0. This edge gets 0, and this edge gets 0. All these edges that go from the set to outside of the set, they get 1. So all these sets get 1, all these edges. And all the edges like these guys that are totally outside of the set, again, they get 0. So really what's going on is that it's the indicator of the cut between S and S complement. Do you see that? For every edge that has one endpoint in S and one endpoint outside of S, you get a 1. Otherwise, you get a 0. So the co-boundary of a set is a cut. So that's nice. So the set of all co-boundaries, B0, the image of delta 0, is the set of all cuts. By this, I mean the set of all functions on the edges that indicate a cut. Okay, so this is B0. Now let's do another example. Let's take some function in C minus 1. Remember, C minus 1 is really just a bit because I just need to say what value I'm giving the empty set. So either 0 or 1. So now what is delta minus 1 of f? So let me just write minus 1 here. So delta minus 1 is for every vertex. I'm moving now from the empty set to the vertices. For every vertex, I need to take the empty set and sum it. Well, I just copy the value. So if it was 0, every vertex gets a 0. So I get the all 0 function. And if it was 1, every vertex gets a 1. That's it. So the set B0, yeah, I guess I should have called this guy B1. Sorry, this was wrong. This is B1 because my convention is that the index says where you are living. So these are functions on the edges, so they are B1 over here, whereas these are functions on the vertices, they are B0. So B0 is just the constant all 0 function or the constant all 1s function. That's it. Okay. And here's another example. Let's look at Z0. These are the co-cycles, the kernel of delta 0. Okay, so these are functions on the vertices such that when you apply delta to them, you get a 0. So delta of a function on the vertices is a function on the edges. Delta of uv needs to be 0, and this is equal to f of u plus f of v. So what does that mean? It's functions on the vertices, so that for every edge, f of u plus f of v equals 0. So for every edge, if f of u is 1, f of v must be 1, and f of w must be 1, and so on and so on. The entire connected component needs to have the same value. Okay, so really what's going on here is f is in this kernel of delta 0 if it is constant on each connected component. If the graph is connected, f just needs to be constant. So it's going to exactly equal B0, right? B0 was the set just containing the constant functions. Okay, so if the graph is connected, we get that the 0th cohomology, remember we defined it to be Z0 divided by B0, the difference between coming from below and being in the kernel of the next, this is just 0. If the graph is connected. If it's disconnected, then they're not the same. So the cohomology measures kind of this being not connected. Sometimes people like to say it measures the holes, but this is intuition that's more correct for real valued functions and less so for F2, I think. Okay, now let's let's look at this example, which is, I think, a bit interesting. Let's look at this graph that I copied from upstairs. Now I'm gonna move it back. Let's look at this graph. Oops. I don't know why this. Okay, never mind. Okay, I look at this graph and I ask myself, my claim is that this function that's highlighted, the yellow, it's a function on the edges, right? It's a function that's 1 on all the yellow edges and 0 on all the other edges. Now, my claim is that it's a co-cycle, meaning that when you apply delta to it, move it up to the triangles, you're going to get 0. Let's check this. So, for example, on this triangle, when you apply delta, you're summing the function on all 3 edges. But since you have 2 edges with a 1 and 1 edge with a 0, you're going to get a 0. So you get 0 here. You're going to get 0 on all of these. What about on this triangle? Of course, you're going to get 0, right? Because you get 0 plus 0 plus 0. So delta of this function indeed is 0. So it's a co-cycle. Now the question is it a co-boundary? We know that B1 is contained always in Z1. But is this a co-boundary? Okay, well, if it's a co-boundary, it must mean that, one of the endpoints of this edge must be inside. There's going to be a set of vertices so that when you apply delta to it, you get our function. That's what it means to be a co-boundary. It means that it's delta of some function on the vertices. So we start with this. Suppose it's this guy. It could have been this one, but let's assume it's this guy. Then this one is in. Let me actually use. This one must be inside. So this one is outside. So this one must be inside, outside, inside, outside. I reached a contradiction because I wanted this guy to be inside, and now I got that it's outside. This is the same vertex. And if you try the other one, you'll get the same thing. So in this case, for this complex, you actually have a non-trivial co-cycle that's not a co-boundary, and in general, you can have much more interesting things. Okay. All right, so now that we have some warm-up, let's try to define a co-boundary expansion. I know we're getting to the end of the lecture, and I know it's a bit abstract, and I hope it still makes sense to you guys. All right, so I want to talk about co-boundary expansion, and the first thing that I want to say is that it's also a generalization of edge expansion. So I defined in the beginning of the previous hour, what does it mean for a graph to be a spectral expansion? I didn't even define edge expansion, but we've all seen it. This is one of the definitions of edge expansion. It basically says if I have a graph G, the edge expansion is the minimum size of a bottleneck. So a bottleneck is like you cut the graph into 2 pieces, S and S complement, and you look at how many edges cross between S and S complement. This is this part, and you divide it by the size of S. When you think of S as being the smaller part, but really you're dividing by the minimum of S and S complement. So this is a standard definition of edge expansion. And now we can rewrite it in a weird cohomological way, but it's actually exactly equal. So that's kind of cool. So what's going on here? Now I'm looking not at a subset of vertices, but rather at a function on the vertices that is not in B0. So what is B0? It's the constant functions, right? Let me scroll up and hope that that's what we got. Right? This is B0. These are the functions that came from the -1 dimensional phase. Okay, so I'm looking at a function on the vertices that is not constant. This is the same as saying a subset that is not a trivial subset. It's not the empty set and it's not the complete set. Okay. And now what I'm measuring is the weight of delta F. Now, what is delta F? It's exactly the cut that is created from the vertices that get a 1 to the vertices that get a 0. So it's exactly, the size of delta F is exactly, the edges that are counted when you count how many edges cross the cut. So this is exactly equal to this. And finally, we are looking at the distance between our function and B0. B0 is the constant functions, the all ones or the all zeros. So what is the distance of my function from the all zero and all ones? Well, if the function has less than half ones, then the closer one will be the all zeros, and you're just going to measure how many ones. If the function has more than half ones, the closer function will be this one, and the distance will be how many zeros. So it's really just the size of either S or S complement. So I managed to parse all of this notation and show you that it's exactly the same thing. But now I want to explain it in a way that makes sense. So it's not just about rewriting this notation. There's actually meaning here. So I want to explain it. What's going on here is that this definition makes sense when Z0 equals B0. So all the functions that are in the kernel of delta are actually functions that, wait, is this correct? Of delta 1 are actually functions that come from below. Why not? Yeah, so we are talking here, in this case, this just means, as we said, that the graph is connected. We said that when the graph is connected, then B0 equals Z0. So in this case, what we're trying to do is not only ask, is our function constant or not? We're actually trying to understand, how far is it or how close is it to a constant function? And the way we're going to do it is we're going to choose a random edge and compute delta on it. So we're just going to see if the two endpoints of this edge are equal. And the probability that they're equal is exactly measured by the weight of delta F. So you can think of this as a test for whether the function is a constant. This is in the top part of the quotient. And in the bottom part, you are looking at the distance of F from, in this case, the constant. So really, this is like a property testing for being inside this set. This is kind of a non-interesting set, so it's a bit of a leap to see it. But the point is that you have this property, and you can test if your function is inside this property by looking at a random edge and seeing if the two endpoints are equal. Now, if your graph is connected, then this test is a little bit good because, if the function is not a constant, there's at least one edge that will notice. But if your graph is like a long path, there might be only one edge that will notice this. But if your graph is an expander, a constant fraction of the edges will notice, at least in relation to how far your function is from constant. Okay, so I didn't say it very nicely, and I only have 5 minutes. So let me move on just to the more general, because this is where it becomes more interesting. Yeah. In greater generality, you're looking at this chain of arrows. This, I want to draw it here. So I have, I don't know, C I minus 1, and then I apply delta, and I get to Ci. And then I apply delta again, and I get to Ci plus 1. Okay, so this is the picture I have in mind. And now what I'm looking at when I look at this expression over here, I'm looking at, I have a function f, it's in Ci, it's over here. I apply delta to it. So delta, it's this map. For example, if the function is on the edges, then for every triangle, you sum up 3 things. So it's a very, very local map. It just looks at f on 3 queries, kind of XORs them and checks. And the weight of delta f is how often you get a non-zero. Okay, this is like the test is rejecting. It's supposed to be 0. If it was all 0, then you would actually be, in the kernel, like here. But the test is rejecting sometimes, so you have some non-zero points, and you want this to be comparable to how far you are from being a perfect solution that maps exactly to 0. So really what's going on here is that you think of this as some kind of a property, and you're comparing your distance to the property versus how much the test rejects or doesn't reject. So I'm sorry that I skipped a bit fast now, but the takeaway from this is as follows. For the case of I equals 0, the definition of coboundary expansion, this quotient that I have over here, is exactly coinciding with edge expansion. Now, when you increase I and you move to functions on the edges, on triangles, and so on, you get something that looks completely new. And it was studied in different contexts, like it was studied for a property called the topological overlap by Gromov, and now we know that it's connected to distance of quantum codes, for example. But in a really cute paper, Lubotsky and Kaufman showed that really what's going on is that this definition is a definition of property testing. It's showing that if this quantity, this HI, is lower bounded, say it's a constant, it means that you can measure the distance of F to your property. And I know I have here 2 definitions. One is the distance to ZI, one is the distance to BI, and I'm not going to go into it now. You can measure the distance of your function to some complicated property by doing this test, by computing delta at a random point and checking if it's 1 or not. Okay, so it's like the coboundary expansion of the complex is equivalent to property testing of this specific property. And somehow this leads to these locally testable codes and to a lot of interesting things. Okay, and I guess that's all I have time to say now. Thanks for your attention. I know this is a bit kind of off to the side of the focus of our semester, but maybe I can also comment that when you try to prove, property testing, you want to prove you want to prove, say, a lower bound on HI for certain complexes, like for the spherical building, for example, that we saw, or for other things. To prove these things, the way we know how to do it, you really rely on all these analytic tools, the random walks, spectral bound. So it's not a coincidence that these 2 things live on the same object. You kind of want to use all the power from both these different definitions. Okay, I guess if there are questions, I'm happy to take them.
Thank you very much, Irit. Any questions? So any questions from the audience?
I was wondering if there's connections between coboundary expansion and spectral expansion. In particular, if you have very strong coboundary expansion, can that imply spectral expansion? Is there anything known of that kind?
Okay, great. Thanks for the question. Yeah, there's a few things known. One really interesting result of Wundert and Wagner shows kind of a disconnect between the 2. They give a complex where you have great spectral expansion, but no co-boundary expansion or even no co-systolic expansion. So that's kind of too bad. But on the other hand, a celebrated theorem of Kaufman, Kashdan, and Lubotsky, and also Efrain Kaufman, show that if you know spectral expansion in the links and you know co-boundary expansion in the links, then you can deduce, I want to say global co-boundary expansion, but you can't, you can deduce global co-systolic expansion. You see here that I haven't kind of talked about the difference between the two, but basically let's think of them as the same. So you do have this local to global theorem, but which uses the spectral, but it also uses the local linear algebraic thing. Yeah, and kind of one wonders, this result of Gundert and Wagner that gives a kind of a counterexample. Maybe there's a way around it. So I don't know.
Any more questions from the audience?
Do you know if there are any applications of expansion, like spectral expansion to topology, like, I don't know, to upper bound the dimensions of the cohomology groups and stuff like that?
Yeah, so maybe I should have said that actually. Thanks. This trickle-down theorem, which is the first theorem that I showed, that shows you how spectral expansion in the links implies spectral expansion of the global underlying graph. So really what, people that know attribute this theorem to Garland from the 70s. And I mean, he didn't prove it in this generality. He proved it for a more specific complex where he tried to, and he succeeded, to show that the real valued cohomology vanishes and use the expansion of the links. So he did it exactly on these Brotitz buildings that are like what we talked about, the Ramanujan complexes, where the links are spherical buildings. So you have good expansion there. And he proved that the cohomology, but it's a real valued or integer valued cohomology vanishes. I don't know if that's what you meant, but anyway.
That's a good answer. I wonder if there is something similar for small set expansion, but be something to investigate this semester.
Yes.
Thank you, Noam. Any last questions? Okay, if so, let's thank Irit again.
Okay. Thank you, and have a great semester, and see you.
So thank you, Irit. So we'll return after lunch when Noam will be speaking.